hand it over to Jorge to transition to the second hands-on session.
All right, thanks.
Thank you, Ken. Thank you, Jason. Yeah, we have a second hands-on session. I will share my screen and then I will let Elie lead this session. Hopefully this will go smoother than this morning. We'll have a hands-on session on TCP bandwidth delay product. We talk about BDP, the bandwidth multiplied by the delay, and that's a number that is quite relevant because the TCP buffer and the router's buffer size use this number. So Elie will go through these labs. The PowerPoint slides are already online, and we will be uploading the rest of the PowerPoints later during today. Now, if you didn't enroll yet for this hands-on session, this is a different library than Persona. So please feel free to do it. Here we have the URL. Now, this sub-library, we will not cover all, but there are many other topics that might be of your interest. For example, what type of congestion control, what is the performance of different congestion control algorithms. There are several labs that might be of your interest. And this will be available after the workshop as well. So I would let Elie to share. Elie, could you please share your screen, and I will briefly introduce you.
Sure.
So Elie is a PhD student here in the College of Engineering and Computing at the University of South Carolina. He's doing research on P4 programmable switches, buffer sizing, dynamic buffer sizing. He's working in several projects. Before coming to UofSC, he received his master's degree in computer science from the American University of Science and Technology. Elie, please feel free to proceed from here.
Thank you, Dr. Kfoury, for the introduction. So hello, everyone. On this hands-on session, we will be going over some tools that are very relevant whenever we want to emulate wide area networks. And we will see some recommendations whenever we want to tune our end devices to get better throughput. So we will be briefly describing the platform we're using. Specifically, it's called MiniNet, Iperf 3. Why TCP buffers are important, what is a BDP and the TCP window. And then we will later on during the hands-on session, we will see what happens if we don't tune those send and receive windows. And then after we tune them, what is the throughput gain that we have. So I will skip over this. Dr. Jorge mentioned it. This is the list of labs that are available in this lab series. So in this lab series, we decided to use MiniNet. MiniNet is a software that allows us to perform network emulation. And basically, we will be using real Linux network stack for the end hosts. So sometimes we call these containers, but more accurately, it's called network namespaces. So the devices like the hosts here in this topology will be inside network namespaces. And the containers consume sufficiently few resources that networks over 1,000 of nodes have been created running on a single laptop and also achieving very high rates. To be able to create the topology, we will be using a graphical user interface editor called MiniEdit. And in this editor, basically, you can drag and drop these different devices and make the connections as you wish. Some of the devices that are available there are hosts. So these are regular Linux-based hosts where you can issue any Linux command. You have also switches. You have software. Both of these are software, actually. So software switches, software routers, and basically, you need to connect them through links. Once you have that topology there, you can click on run, and this is going to be deployed on your machine for emulation. Now, in our labs, we already created the topologies and they are saved in files. So we will just load them. We don't have to recreate the topology for each lab. This is an example here with the minimal topology in MiniNet. So we have one switch and two end hosts. And if you want to emulate something like this, all we have to do is just insert two end hosts here, H1, H2, have a switch, and then basically connect them. And once we have it, we click on run, and the devices are ready to start communicating. So if you try a ping test or an Iperf, it will work immediately. Now, the default IP addresses that are used are in the network 10.0.0.0/8. And the convention here in MiniNet is to use the host IP here .1 based on the host name. For example, H1 will have 10.0.0.1, H2 will have 10.0.0.2. If you have H3, it's going to be .3, and so on. So a brief introduction on Iperf 3. Where is Iperf 3? Iperf 3 is a real-time network throughput measurement tool. It is open source and is client server based. So we have to launch a server for listening to incoming connections, and the incoming connections will be basically Iperf 3 clients. So we can basically say that I want to start a server on this host here and a client to connect to that server, and we'll start pumping data. And based on the throughput, we will get a report at the end of the test telling us the amount of throughput that we got during that test. And Iperf is interesting because of, we can measure the throughput, and it will allow you to troubleshoot a lot of problems as we've seen in the previous slides. It can operate on TCP, UDP, SC-TCP. It can work in both directions. It can be unidirectional or bidirectional. And this is an example here of a report produced by Iperf 3. So you have the intervals, and then you have the bit rates achieved per interval. And also you can see the total amount of bytes transferred for that test. So we will be doing lab number 8 in the series, which talks about bandwidth delay product and TCP buffer size. Just to give a brief overview on TCP buffers. So TCP has the send and receive buffers, and they can greatly impact the performance of data transfers in a wide area network. So on the sender side, so we have a TCP send buffer. TCP will accept the data from the application, and the data is placed in the send buffer. Typically, it's based on the maximum segment size. In this example, it's 100 bytes. And then these segments will be transported over the network and sent to the receiver. Now, once it reaches the receiver, they're going to be received at the TCP receive buffer. And then this data is delivered to the application in order. Okay. And basically, the receiver will be sending back the acknowledgement for the segments that are being sent from the sender. And the idea is these buffers here, their space, or how much available space you have, will basically give us an idea on the throughput. So the receiver will be basically indicating the sender how many bytes they can send based on how much free space you have in the receiver. So this is why the buffer size here in the TCP send and receive can impact the performance of the network and the throughput that you can achieve. Just to give some few numbers, if you are assuming that we have a TCP buffer size of 1 megabyte and a round trip time of 50 milliseconds, and also if you assume that we have a 10 gigabits per second link, then the value of bytes inside this buffer, which is around 8 megabits, will be transferred in 0.84 milliseconds. And this means that after 0.84 milliseconds, so this data was transferred, the TCP send buffer will be empty, and it must wait for the acknowledgement from the receiver. And because we have a 50 millisecond round trip time, so we have to wait for 50 milliseconds to receive those acknowledgements. And this means that the sender will only be using a very small percentage of the available bandwidth. In this specific example, around 1.6%. So tuning these buffers is very important to get the throughput that you are aiming for. So how can we fix that? What value should we set this TCP send and receive buffers to? So we have the quantity, the bandwidth delay product, which is basically multiplying the bandwidth by the delay or the round trip time. And basically this number of bits is the value that can be transmitted in a round trip time period. So here an example for the same setup that we've been using in the previous slide. We have 10 gig, we multiply it by 50 millisecond, and we get around 62 megabytes. So this is basically the bandwidth delay product. And we want to make sure to set the TCP buffer size to at least 1 BDP. Now, in Linux, there are some observations that you have to keep in mind whenever you send and receive buffers. Linux by default assume half of the value that you set for internal structures. So if you are planning to set it to 1 BDP, you have to set it to 2 BDP so that you are really using 1 BDP for the TCP buffer size. So in our case here for 60 megabytes, we will be setting 120 megabytes. This is the topology that we'll be using in the lab. So we have 2 switches, we have 2 end hosts, and there's a bottleneck link of 10 gigabits per second. So we will also see how we can configure this bandwidth here to be 10 gigabits per second. And also we have 20 milliseconds of round trip time. So also we will show how we can configure this round trip time, how we can emulate it. And then if we just run a Iperf test at this point, we will see that the throughput that we will get is around 3 gigabits per second, which is far from what we configured, the value of 10 gigabits per second. And this is because of the TCP send and receive buffers are not properly configured. Then we will show how we can modify them in Linux. So we will see this command, and I will explain it as we go through the lab. And later on, we run a test, the same test we run again, and we will see that we will be able to get the maximum throughput, which is around 10 gigabits per second. So this includes the set of slides. I can now move on to the hands-on session. So again, we are doing lab number 8. I already made the reservation. If you haven't done so, please just use the link in the website next to the session number 2. And then make sure to click on lab number 8, bandwidth, delay product, and TCP buffer size. All right, so like the other labs,
Elie, do you want to wait for maybe 1 or 2 minutes to give time?
Yeah, definitely.
Everyone.
Definitely.
So you're going to go through this lab number 8, which is the bandwidth delay product, but you will be explaining much more than BDP, right?
Yes, I will be explaining Iperf, how to emulate the wide area network, so how we can emulate delay, setting the speed of the link, and other commands as well.
And all these labs, I mean, there are, for the lack of time, we will not go into much detail. Elie will not go into much detail in for example, NETEM, which has several parameters, or the token bucket filter. All these are tools that are provided by Linux. But those tools are described in several other labs. Like lab number 3 or 4 is NETEM, lab number 5 is token bucket filter, etc. So if you want to get more information about these tools, they are all available in the different labs. Yeah, I think we can proceed, Elie.
All right. Okay, so what you can see here now is on the left-hand side, I have the a manual, and on the right-hand side, I have the machine. So in this series, we are only using one virtual machine. So if I go here to the pod, you will see that we only have client 1. And this is basically the machine that I'm showing on the right-hand side. But inside that machine, we will be emulating the whole network instead of having multiple machines here in the pod. All right, so so the lab start with first a table of content just to show the different sections. At the beginning of each lab, we have an overview, the learning outcomes, the objectives of the lab. We have a table that describes the credentials of the machine. For this machine, we have the username admin and the password, all small caps. And we will be basically using those as we perform some commands that require higher privilege. Then we have the introduction, which discusses basically the theory behind all the topics that we will do in the hands-on. And you can see here, we are talking about TCP buffers, bandwidth delay product, the observations when setting the TCP buffer size in Linux, and other topics as well. So if you want to go in details to understand the idea behind all the practical topics later on, you can read this introduction. It will give you enough background to go over the lab. So starting from section 2, this is where the hands-on starts. And this is the topology that we will be using. So we have 2 switches, 2 end hosts, and we will be emulating those in Mininet. So the first step is to start.
Elie, can I interrupt you for a second? So
Sure.
Christopher has a good observation. He said, my learning area just has workshop on networking topics dash perf sonar. So do you wanna, or Jose, if you're there, do you wanna show how to access to the network tools and protocols labs?
Sure. I will post the enrollment link in the chat. And you can click on that. And if you are already enrolled into the persona, it's just a matter of clicking on this link and it will be added to your course and to your course list in the next login.
Okay, so yeah, Chris, you have Jose just share the URL. Just click there and you will have access to the 8 to 10 lab, or actually 20 labs probably. And Elie is going through lab number 8 right now. Apologize, Elie.
No problem. Shall I proceed, or should I wait a little bit so that everyone makes the reservation? And
yeah, let's wait 1 minute. Perhaps there are some that are.
Sure.
So Brian, this is just the topology. Elie, I don't know if you shared your topology. It's just one client. Probably is a good idea. I don't know if this will derail you, but if possible, you can show from the beginning when you start in a different browser maybe.
Yes, sure.
And also we will share with the Bill. I will share here the full lab series PDF. Again, Bill, I will share with you in a second.
So I'm using the link that is available on the website next to the hands-on session 2 enroll. And this should take you to the NDG portal. Okay, so once you are there, you should log in using your credentials. And from there, you will see the list of courses that you are enrolled in. So in this case, we are going over the NTP, Network Tools and Protocol. So I will click on that. And here you will see the list of labs from lab 1 to lab 20. In this hands-on session, we are going over lab number 8, which is bandwidth delay product and Tcp buffer size. So you click on that. And basically what you would see here is the pod. This is available. So you can start now by running the experiment. You click on the client one, and now you are inside the machine. Okay. And the content can be seen here in the content button. So what you can do is, as I was doing, you can open it in a new window, put it aside, and then basically put the other window which contains the machine on the right-hand side. This way you can follow both pretty easily. Is there any question regarding accessing the platform?
I think we're good, Elie.
All right, thank you. So basically, we talked that the first part is just the theoretical background. We are now in part number 2, which is the lab topology. So I will first start by clicking on the client 1 to enter to the VM. And from here, I will go over step 1, which is basically launching MiniEdit. Again, MiniEdit is the graphical user interface to edit the MiniNet topology. And there's an icon on the desktop that you can double click on it. And it's asking us for a password. So the password here is password all small caps. Okay, so once you type in the password, you hit enter, you should see the MiniEdit screen. Now here, where I was telling you that you can basically drag and drop these devices and create a custom topology. But to make things easier for us, we already created the topologies for each lab. And what we're gonna do now is open the topology that we already created. This is step number 2. And to do so, we have to go to File, then Open, and then select the lab number. So File, Open, and we are going over lab number 8 now. So I'll click lab number 8 and then click on Open. Now we can see now we have 2 switches and 2 end hosts loaded in our topology. And this is the topology that we were talking about using, right? So we will have 2 switches, 2 end hosts, and next we're gonna be running the throughput test and all the other kinds of tests, basically. Now, at this time, we just loaded the topology that we want to run, but the topology hasn't started yet. And to start this topology, we have to click on the run button, which is at the bottom left of the screen. Once we click on the run button, the icons here should be grayed out, which means that the topology started. So now we can no longer use or drag any of these devices in our topology. As a quick reminder, so the topology uses 10.0.0.0/8. This is by default assigned by MiniNet, and therefore host H1 will have 10.0.0.1 and host H2 will have 10.0.0.2. All right, so now we have our topology started. We can start by going over the end hosts and see what we can do there in their terminals. So the first step is to start the terminal of host H1. So step number 1 is to start it. The way to do so is we have to right click on the host H1 and we have to hold the right click. So make sure to hold it, otherwise the pop-up list will disappear. So click on it, right click on it and hold the right click and then select terminal. And you can see here that we have now a terminal dedicated for host H1. And here you can issue basically all kinds of commands that you have on your machine. So you can use ifconfig, for example. You can use ping, you can use traceroute, any kind of command that you use on Linux, you can use it now in this terminal. And the command that you write will be issued from host H1. Okay. If I want to give an example, I can type in ifconfig, and you can see I have the information about the interfaces that we have. So the interface name is H1ETH0, and this is the IP address that is assigned to that interface. So I will apply now the same steps to open the terminal of host H2, which is basically right-clicking on host H2 and then selecting terminal. So now we have a terminal for host H2 and another terminal for host H1. You can retrieve back those terminals. You will find them here in the start bar. So you can select H1, and now you are in H1, and you can shift between the two to select which device you want to perform the command from. The first step is to just try to see if we have connectivity between the two devices, and we will use the ping command to do so. So we are in step number 3. We're going to try to ping from host H1 to host H2. And we know that host H2 has the IP address 10.0.0.2. So I will start by typing in ping 10.0.0.2, and I will hit enter. And we can see that we have some replies from host H2, which means that we have successful connectivity between the two devices. To stop the test, you can simply press on Control-C. And at this point, now we are sure that the topology started well. We have connectivity, we have IP addresses assigned. Next, we can proceed to emulating the link speed and the delay that we want to introduce to our network. This is going to be done in section 2.2. So now we're going to start by assigning some parameters to the link, for example, setting the link speed or the bandwidth, and also introducing delay. And to do so, we want to make sure not to issue the commands from the terminals of host H1 and H2, because we are dealing now with switch S1 interface, which is here on the right-hand side, right? So we want to make sure to configure the network parameters on this interface. And to do so, we have to go to the terminal of the whole VM and not to the terminal of host H1 or host H2. So if you click on the show desktop button here, this is going to minimize everything. And you will see that you have a terminal icon on the desktop. Okay. And again, this is the terminal for the whole VM that we're using. So I double click on it, and now we are inside the terminal. And again, here, this is a regular Linux terminal, so you can issue any command. What we're going to be using is a tool called TC, which stands for traffic control. And this tool will allow us to basically emulate some conditions for a certain interface. So the first step is to introduce some latency, and we're going to be introducing 20 millisecond delay. Therefore, we will have, after we issue this command, we will have a round trip time of 20 milliseconds. So the command that we're going to type is this one. So I will explain as I go over it. So sudo for issuing the command with higher privilege. TC, this is the traffic control tool. QDisc, which stands for queuing discipline. So we are assigning these different kinds of queuing disciplines for a certain interface. And then we want to specify that we want to add to the device, so add dev, and then the interface name. So just to be clear, we have here S1-ETH2, and we are talking here in this interface about S1's interface facing S2. So we are basically emulating the latency here at S1's interface facing S2. Okay. So add dev s1-eth2. And then we want to create a root handle so that basically once we emulate the delay, we will be able to also use that same handle to emulate other things, such as basically configuring the link bandwidth. So I will give it root here, and I will give it a handle. And again, this root handle will be used later on when I want to add another queuing discipline to that same interface. Okay. So now we have to specify what kind of discipline we want to add. So our goal here is to introduce some delay. And there is a very nice tool in Linux called NETEM, Network Emulator. It allows you to emulate different kinds of conditions, such as packet loss, delay, packet corruption, packet reordering, jitter. It's very flexible. You can basically do a lot of configuration so that your emulated network can match as close as possible to a certain production network. In our case, we're going to be using here just the delay. So I will write netem delay, and I will give it a value. In our case, we are emulating 20 milliseconds. So I will type in 20 ms. Now, in case you want to add packet losses, then all you have to do is space loss, and then you add the percentage of packet loss, right? And there's like a large list of conditions that you can emulate, but for now we are just using the delay. I press on enter, and it's asking me again for the password. The password here is password all small caps. All right, so at this point now, we emulated the delay on the interface. What we're gonna do next is modify the bandwidth of the link that is connecting switches S1 and S2, and we're gonna set it to 10 gigabits per second. Now, to change the bandwidth of a certain link, we can use a queuing discipline that is called TBF. TBF stands for token bucket filter, and it's a very well-known classic way of basically specifying a certain rate. You have to give it some parameters, such as what is the rate that you want to configure. In our case, 10 gig. There's a parameter called burst that you have to configure it as well. So how can we get this value? Basically, this is discussed in lab number 5, but basically a good rule of thumb is just to divide the rate that you want to configure by the clock rate in your system. This is going to give you around 5 megabytes. And then you have the limit, which is basically how big your buffer size is. Okay. In our case here, we are setting it to 25 megabyte. All right. And we start by typing this command in the same terminal. So sudo tc qdisk. Notice how so far it's all the same. Add for the same interface s1-eth2. But now what we're going to do is we're not going to create a root one. We're going to instruct tc to attach this TBF to the already created netem there. And we know that we created netem with a handle 1. So we have to tell it now, use parent 1. Again, this one here corresponds to the handle that we created. And give it a new handle for this TBF, which is 2. So again, we are just creating this TBF now, and we are attaching it to the same queuing discipline that we used before, which is netem delay 20 milliseconds. Okay. Next, we have to start by specifying what is the queuing discipline. In our case, it's TBF, token bucket filter, and the parameters for TBF. So we have the rate. We want it to be 10 gigabit. So 10 gbit. You can also specify in megabit. And then the burst size, which is 5 million. And finally, the buffer size, which is indicated here with the keyword limit. And this is 25 megabyte. And I hit on enter. Okay. So what we've done so far, we configured the interface S1 ETH2, which is the interface of the switch S1 facing S2, to have 20 millisecond delay. So we are emulating 20 millisecond delay, and we are setting the rate to be 10 gigabits per second. We also specified the buffer size for that interface. Now we're gonna proceed and test some of the configuration that we've done. So first, we're gonna run the same ping test that we did in the at the beginning of the lab, and this is gonna be executed on the terminal of host H1. So make sure to open the terminal of host H1. Again, you can select it here. So it will show you specifically host H1, host H2. So I will go to host H1 and type in again ping 10.0.0.2. And then I will hit enter. And you can see how now the round trip time is 20 millisecond. And basically also you can see previously it was very small, and now we were able to successfully introduce or emulate this 20 millisecond of round trip time. Okay. I will press Ctrl+C to stop the test. And we can proceed now to test the throughput. And we know that ping is used for latency. We can use Iperf 3 to test the throughput now. And this is step number 4. So remember that we talked about Iperf 3. This is a client server application. So before we start testing the throughput, we want to make sure that the server is listening for incoming Iperf 3 clients. Okay. And in our scenario, I'll go back to the topology. What we're going to do is we're going to set host H2 as the server and host H1 as the client. So host H1 will be sending data to host H2. Okay. To make host H2 as an Iperf 3 server, we have to go to the terminal of host H2. So again, make sure to select host H2. And there I will start Iperf 3 in server mode. For those of you that are receiving this pop-up, which means that the reservation might end soon, you can simply press on request more time, and this is gonna extend your reservation. Okay, so let us start now Iperf 3 server on host H2. I will type Iperf 3-S, -S for server. And now we're gonna start Iperf 3 in client mode, but now we're gonna do it on host H1. So this is step number 5. We have to go back to the terminal of host H1. And from there, type in the command Iperf 3-C, and then the IP address of the Iperf 3 server, which is the IP of host H2, 10.0.0.2. And I will hit enter. And by default, Iperf 3 will run a test for 10 seconds, and it's showing us the bitrate for every 1 second interval. And also it's showing the amount of bytes sent. So what we should get from this output is that we are achieving on average a throughput of 2.6 gigabits per second. But we tried to configure the interface to 10 gigabits per second. And there's a reason why we are reaching this throughput and not the 10 gigabits throughput. Okay. And the reason is the TCP buffers are not properly tuned. So we want to make sure to tune them well and then repeat the test and see if we can get high throughput. Okay. Iperf 3 can be used for a lot of other tests as well. So we can use it in UDP mode, TCP, and maybe we can start multiple servers and run more complex tests. But the goal here is just to show you that if you just out of the box have a 10 gig link, when you don't do any tuning to the end hosts, you won't be able to get the full throughput. You have to perform some changes. And what is important to know is that the changes that we're going to describe next are exactly the same thing as you would do in a real server. So we are not only talking about MiniNet emulated device. These are the same configurations that you have to do on servers that you just use in your network. Okay. So moving on now to section 3, which is the BDP and the buffer size. So this is where we're going to see how we can inspect the send and receive buffers that are being used by TCP. And we will see how also we can modify them. So in Linux, there's the Cctl tool, which many of you might already be familiar with because it's used to basically tune many of the kernel parameters, not only TCP specific or data transfer specific. So there are some parameters that you can change using this Cctl tool. One of them is the TCP receiver window size or TCP buffer, and also the send buffer. And they have different keys basically. So let us start with step number 1, which is to see what is the currently configured value for those window sizes on host H1 and on host H2. So first we will start with host H1. We are there. This is the terminal. I can type in sysctl. So I'm typing in now this command here. Sysctl net.ipv4.tcp_rmem. And this is going to show us 3 values. So we have the minimum, that's the first one. We have the default, and we have the maximum. And those are represented in bytes. And we can see here that the maximum buffer, TCP buffer that is configured is around 16 megabyte, which is lower than our bandwidth delay product. And this is kind of telling us why we can't really achieve this 10 gigabit. Now, same thing you can do to check now the send buffer, which is exactly similar, but instead of using RMEM, you use WMEM. And we can see here also these are the same values. And by the way, the values that you see here are the default ones in Linux, at least in this distribution in Ubuntu, right? So if you are using this out of the box, that's the currently configured buffer size, and you need to make sure to modify it. All right. Now, we talked about our bandwidth delay product. So we have 10 gig link, right? We configured a link of 10 gigabits per second, and we have an emulated round trip time of 20 milliseconds. And so if we do the math, so if we just multiply these two quantities, we will get the bandwidth delay product. So it's 10 gig multiplied by 20 millisecond. And the bandwidth delay product is around 25 megabytes. Okay, so we want to make sure to configure our buffers to a value larger than this so that we can attain the full throughput. Okay, now we talked a little bit about this in the slides, but I'm going to repeat it again. In Linux, by default, whatever value that you specify here for these buffers, only half of it will be used for your applications. The other half will be used for other internal structures. So if you want to use 1 BDP, you have to make sure to multiply it by 2, right? So you would eventually set 2 BDP here. Okay, and then the Linux will be using half of it, which is 1 BDP, and this is going to be used for your application. So 1 BDP is around 26 megabyte, and then 2 BDP is around 52 megabytes. So we will configure the send and receive windows to have a maximum value of 52 megabytes. How can we do this? We have to use also the Cctl tool, but now we have to give it the -w, which means that we want to write some value to a certain field. And then you give it the key, which is net.ipv4.tcp_rmem equal, and then the value. So Cctl works in a key value approach. So the key is here in this case, the TCP_rmem, and the value is whatever you write after the equal. So we're going to keep the minimum and the default as they are, which is 10.240, and then space 87.380. And now we're going to change the maximum to be around 52 megabytes. So 52428 8800. You don't necessarily have to have it exactly that. So if you type in basically 50 million, it should do the work, right? But we are just showing how when you do the calculation, you'll be able to determine that value to be placed there. Now, another important point is that many times you don't want to be repeating all of this again and again. So you need to have it persistent. And the way to do so, there's a file. I can open it here. It's in /etc cctl.conf. Okay. And basically this file contains all the fields that you want to override. So if you want to decide to use this send and receive buffer at all time without having to reissue that command again and again, you can basically type in the key and the value pairs inside this file. This way, whenever you turn on your machine, it's going to read this file and then apply the configuration. Okay. All right, so we changed the receive window. Now we're going to do the same, but for the send window. And to save time, I will just use the up arrow. This is going to give me back the previous command that I wrote. And then, so we are basically here in step number 2. All we have to do is simply change the RMEM to WMEM and press enter. Okay. So now we changed the value of the send and receive window, the maximum value to 52 megabytes. Next, we will do the same thing, but on host H2. It's a good idea to always modify both sides of the session because maybe both sides are going to be transmitting data. And you want to make sure that both are not bottlenecked by the value of these send and receive windows. So to modify it on host H2, first we have to go to host H2. Click on host H2 here. We can see that the server, the Iperf3 server is still listening because by default, it will keep listening till you just explicitly stop it. I will use Control-C here to stop the Iperf3 server so that I can issue the Cctl commands. Okay, so let me type now the Cctl on the host H2. So net.ipv4.tcp rmem. Again, we're going to use the default values for the minimum and default. And then we have to use the 2BDP here in this case to the maximum buffer. Okay, and same thing for the other parameter, which is the sending window. I will use the up arrow and change from RMEM to WMEM. Okay, so this is all we have to do to make sure that we are using large buffers. There are some observations that are mentioned in the lab. For example, if you are planning to use congestion control algorithms other than the default one, which is cubic, you might encounter some situation where you want to increase more of those send and receive buffers, especially in an algorithm called BBR. So there is some information in the lab. If you are interested, you can go over it more. But typically, setting it here to 1 BDP should be good for loss-based congestion control algorithms such as cubic, the default one we use in Linux systems. All right, so step number 5 is to proceed and start again our Iperf3 server so that we can repeat the test that we did before. So Iperf3-S, the server is listening. And now we can go to host H1 and restart our client, our Iperf3 client, to see the throughput that we get. So make sure to go to host H1 terminal. And there we will issue the command Iperf3-C 10.0.0.2, the IP address of host H2. Press on enter. And we can see now on a very significant improvement in the throughput. So we are basically achieving the maximum theoretical bandwidth, which is close to the value that we set, 10 gigabits. So on average, it's around 9.37. That you can see at the beginning of the test, there was some losses. This is completely normal, just for TCP to adapt. And then we were able to fill the pipe, the BDP. We have the receive and the send buffers properly configured so that they can absorb this amount of traffic. And this is why we are now fully utilizing our link. So this is the end of this lab. The idea is just to show you that some really trivial tuning that you have to do on the end hosts are very important, and you will see significant improvement in your throughput. In this lab, we talked about the send and receive buffers, but there are other labs that talk about buffer size on the router. There are other labs that talk about congestion control and stuff like that. So it's a good idea to see all the remaining labs if you are interested, to make sure to tune your network properly.
Thank you, Lee. I think there are some observations, and I don't know if you want to address. Brian said, could you throw a -R on there and rerun, please? I'm getting much lower in reverse.
Yes, so let's try it first. Yeah, so we got around 7 gig. The thing that we should keep in mind with this kind of scenarios is that whatever you use on the TBF or NETEM or any of these emulators, they are applied to an interface basically depending on a certain direction. So if you want to maybe run it in the other direction, you have to make sure to apply it to switch S2 specifically on this interface here, and then it should basically work. There should be like some proper or more deeper explanation to this if we do the brainstorming, but I'm sure that if you run it in the other way and you modify it on S2, this should give you the full throughput.
Yeah, very quickly. I mean, without a deep analysis, the test that you did before from H1 to H2, prepare first the bottleneck link was 10 gig in that direction from S1 to S2, but also the buffer size that you set on S1 was large enough from that direction from S1 to S2. I'm guessing that you will have to establish enough buffer also if you do on the other direction.
Yeah, definitely. Yeah, there's a lot of tuning depending on the scenario, but the nice thing about MiniNet is it's fairly easy to deploy complex topologies. And if you just try here to run an Iperf test without limiting the rate, you can get up to around 50 gigabits per second. So it's going to really give you a lot of flexibility in testing with high speed links. And as well, with the combination of NETEM, you can emulate not only delay, but also like packet losses, and you can give the probability of a packet being dropped. So it can really give you like a characterization, if you know your network well, to reproduce that scenario and try to troubleshoot or try to see what you can improve there.
There's another comment or question. Can the emulation be model / hardware specific, or are the switches fairly generic in its emulation? I don't know if you want to address or if you want me to address. Up to you.
I want to make sure that I understand the question correctly. So the commands that we're using now basically are available in hardware targets. So not the same commands basically, but you can, for example, modify the buffer size on some routers. You can modify the link speed and stuff like that. Now, the commands that we're using are purely emulation for these software switches. The one that we are using here are OVS, the Open Virtual Switch, and it's a Linux base, so all the Linux commands available for you there for emulation, you can apply it to them. You won't be able to apply, for example, TBF on the router itself, right? Or NETEM on the router, a physical router, but maybe you can apply it in some other devices along the way, or if they might have like other kind of emulators. I know that there are some physical emulators that can add latency or can change the bandwidth of the link.
I will add to what you said, and you didn't make emphasis on the buffer size, but the third parameter that you were configuring the switch S1 was the buffer size, and that is, for example, the idea is a general idea you are applying to your software switch, but still you see exact or similar effects that what you are able to see on a physical device, and on a physical device you can also set the buffer size. So there are some ideas that translate directly from the software switch that Elie is using to the physical switch, some switches that allow you to do the buffer modification, and others that are a little bit more specific to the software switch. Okay, with this, we are finalizing the program of day one. Certainly, we have a few minutes for questions, discussion. I am sharing in the chat window. We would appreciate if you can give us the feedback for this day number one. It's going to be very useful, so we improve from here. And now I see another comment. In our example, for H1, H2 flow, only send window on H1 and receive on H2 needs to be configured. Elie, I don't know if you want to address that.
Yeah, basically that's correct. Unless if you want to do it like on different directions, you want to make sure to have them both configured.
And again, on the with that, I want to emphasize again, and we would appreciate if you can give us the feedback. Workshop day one survey. The survey is already in the chat window. With that, Jason, Christy, Jeff, I don't know if you want to share something else before we close this day number one.
Just again, our thanks to everybody for sticking with us as we worked out some of the technical issues, and hopefully everybody got something out of today's presentations. And certainly if you think of questions between now and when we meet again on Tuesday, we're available to answer them. But otherwise, we're just happy that everybody can join us today, and we'll make sure that all the information gets posted, and we'll be ready to talk to everybody again in 1 week's time.